Hello everyone, and welcome to today's HPC focused webinar. My name is Mark Clark, and I will be the moderator for this webinar today. Today's webinar is titled Regional Application Profiling with Caliper. Your presenter for today is Florent Lebeau, Staff Solutions Architect from ARM. I'm just going to give you a bit of general housekeeping. So please direct any questions that you may have throughout the webinar into the questions panel, and we will answer these during the Q&A section at the end of today's session. After today's session, please look out for an email that will give you access to the recordings from today. We also do value your feedback, so please complete the very short survey at the end of today's webinar. Right, I will now hand you over to Florent, who will now conduct today's session. Thank you.
Thank you very much, Mark. Hello, everyone. So during this webinar, I would like to illustrate how the latest feature of our map can help to optimize your code faster using Caliper. So first, I will introduce our map, a profiler for HPC. I will briefly explain its usage and benefits. Second, I will present what is Caliper, how it is used, and how it adds meaningful information to your profiling results. Finally, I will show and explain how map and Caliper combined can help optimize the performance of an application. So map is part of ARM Forge, which is a development solution for HPC Expert. Map is a parallel profiler for C, C++, Fortran, and Python applications. It is easy to use. There's no need to instrument your code. The only requirement is to compile it with -G to get source level information. To profile your application, just prefix your execution commands with the map keyword, and it will generate a .map file that you can open afterwards locally or remotely. You can see an example of the profiling result on the screen. Map displays results in 3 sections. The timeline on top with different colors describe the application behavior as it runs. The vertical axis shows the activity per process. The green sections indicate when these processes are computing, and the blue sections when they are performing MPI communications. The source code is displayed in the center and is annotated with time information. The application stack trace is displayed in the bottom of the GUI. Map is highly scalable. It supports MPI, OpenMP, and GPU applications. It is also a cross-platform tool which supports ARM, x86, and Power architectures. So the profile shown on the screen here has been generated without Caliper on an hydrodynamics benchmark developed by the CEA called HydroC. This application runs on 2 nodes using 16 MPI processes for almost 1 minute. With map, it is easy to identify iterative patterns of code, especially if there are MPI synchronization calls, as it is the case here. You can see that the source code annotations highlights that the same function is executed many times. Application bottlenecks can also be easily identified by switching to the function tab. Here, 3 functions correspond to approximately 60% of the runtime. The time activity reported for this section indicate that they are called numerous times and also seem to follow an iterative pattern. The stack view shows that these functions are called in two different code paths. Clicking on the plus sign gives a breakdown of the time spent in this path and helps to understand their behavior. And in particular, which lines of code are the most time consuming. When the time spent in one of these functions roughly corresponds to the execution of 3 lines of code, the 2 other functions have a flat profile, which means that the execution time is spent almost equally on all lines of code. And the problem here is that there are a few hundreds of them, so analyzing all of these lines can be tedious. The question is there a way to understand the structure of the code faster? The answer is yes, and the solution is Caliper. Caliper is developed by the Lawrence Livermore National Lab, and it is an instrumentation-based framework for C, C++, and Fortran codes, which provides application and performance information. Caliper can sample or trace code regions to provide MPI or CPU performance reports. It can also be combined to other profiling tools like PAPI, Tau, NVProf, and now ARMMap. Using Caliper is quite straightforward. A high-level API can be used to instrument functions. For our example, we can add annotations to identify the functions that correspond to the main performance bottlenecks. Additional Caliper annotations can be used to define loops or arbitrary code regions. In our example, the Riemann function, which corresponds to 40% of the execution time, is quite a big piece of code with more than 300 lines. Thankfully, the developers broke it down with comments in the source code that describes what is happening. Let's reuse this information to define Caliper regions and add insight as to how the different pieces of the algorithm run. Caliper is very flexible. A configuration file can be used to specify what information needs to be collected, thanks to PAPI or kubectl, for instance. Various output formats can be generated, like text reports or traces. Caliper comes with tools to post-process the results by generating graphs or query the large trace files. As an alternative, MAP only relies on the Caliper instrumentation. None of the Caliper tool is required. This approach allows users to quickly generate results and complement the rich Caliper ecosystem. Here is the profile of the I2C application with Caliper annotations. We are using the same configuration on 2 nodes, and the runtime is exactly the same. An additional section appears in the GUI. The selected regions underneath the activity displays when processes are running the Caliper sections selected in the Regions tab in the bottom of the GUI. This new profile clearly displays iteration and sub-iteration patterns when the application bottlenecks that we instrumented are running. In addition to the timeline sections, you can see that MAP also displays various metrics like CPU floating point or memory usage, as shown on the screenshot here. These graphs draw the average value of the metric for all the processes, in addition to the minimum and maximum values. Thanks to this, it becomes easy to find regions of code with high floating point computation activity and possible workload imbalance between processes. The profile here shows that the variation of floating point operation seem to match the calls to the Riemann function. MAP can help us investigate further. It allows users to zoom in on a specific time frame. For example, we can zoom in on one iteration of the algorithm. The peak value in floating point activity confirms our suspicion. Different CPU metrics can be displayed, and to understand what type of floating point operations we are performing, we are also displaying the amount of floating point vector operations. Interestingly, this highlights a performance issue. The floating point computations performed by the Riemann function are not taking advantage of vector units. Selecting the code regions inside the Riemann function provide more insight. We understand how the time is split between the various steps inside this function: pre-computing, resolving interfaces, and running the main solver. Activating the regions-focused view makes the analysis of the source code easier by displaying Caliper information for the corresponding lines of code. In addition to the source code, the stack view also displays the Caliper information. It is now easier to understand what these lines of code are doing, and prioritizing the optimization work becomes more straightforward. When selecting a line in the stack view, the code viewer automatically displays the corresponding source file and highlights the selected lines of code. When doing so, a breakdown of the activity of the source line is displayed on the right of the GUI. This is an efficient way of finding out which lines of code were not vectorized, and it is the case in our example. A simple fix can be applied to this performance problem. The use of OpenMP SIMD pragmas can force the compiler to vectorize the sections of code. When profiling the results again, the performance improvement is obvious. MAP indicates a higher amount of floating point and vector floating point operations. When zooming in on one iteration of the algorithm, the correlation between the high amount of vectorization and the execution of the different steps of the Riemann solver underlines the impact of our code change. Naturally, MAP shows that the lines of code that had performance issues earlier are now well vectorized, and we understand which sections of the Riemann solver really benefited from the code optimization. As a next step, we can use Caliper regions to understand how the application behaves when scaling up on 4 or 8 nodes, for example. This is not the case here, but it can potentially highlight scalability issues for some code regions. Similarly, you can analyze how these regions behave on different input data and visually check if the behavior is the one you expect. So we're reaching the end of this webinar, and we have shown you how to use MAP with Caliper instrumented applications. Please note that you will need one of the latest version of our tool, which is now version 19.1.3, to take advantage of this feature. We have explained how to analyze results from the profiler and how it can help tuning your application further. By adding application semantic to MAP, Caliper makes the identification of source code bottlenecks and their optimization faster. If you would like to profile your own applications and evaluate the other features of ArmForge products, you can request a trial license by visiting our website. This license enables all products, all features for all HPC architectures. It also grants access to our support channel. Plenty of resources like our user guide, blog articles, and tutorial videos are also available online, so feel free to check them out. Thank you very much for your attention. We have some time now for a few questions, so please feel free to ask. So I have already a few questions. So does this work on Android from Glenn? So no, unfortunately, map is not supported on Android. I don't think Caliper is supported on Android as well. These frameworks, these tools are for HPC systems, so general Linux, but not Android. Another question from John. Are annotations supported or planned to be supported in Python code? So at the moment, Caliper only supports C, C++, and Fortran. So I don't know if they have plans to support Python annotations for Python. So at the moment, we only support the language that a Caliper can instrument. So in terms of limitations, I've got a question here. Are there any known limitations? So there are some limitations indeed. Caliper actually uses different APIs. So map only supports the high-level API in C, C++. And for Fortran, the low-level API is supported to emulate the high-level API. So you need to make sure that the Caliper regions are nested. So that means that the inner regions need to be closed before the outer regions. Regarding the overhead of using Caliper and map together, there should not be any particular overhead when using map in addition to Caliper. However, be careful when instrumenting fine-grained loops. Profiling them can be intrusive and result in a significant overhead. Regarding multi-threaded applications, so it is possible to use Caliper and map together for OpenMP codes, for example. But note that at the moment, map will only report the Caliper information of the corresponding processes, but not the threads themselves. So another question from Wusan. Does Caliper work with perf reports too? So no, unfortunately, the information, the Caliper information are reported in map only. So no Caliper information in perf reports at the moment. And there is another question from Glenn, if our tools support Java. So no, map doesn't support Java. You can probably get some information though, because as I said, one main requirement is to instrument the code by compiling it with -G. So obviously you won't be able to see any Java information, but possibly you can get some profiling information without the link to the source code. This is something that you can try on Java. But yeah, just be aware that you won't be able to take advantage of all the features of map with Java.
Okay, do we have any more questions coming through?
No, I think that's all.
Okay, all right, if that is it for the questions, I'd just like to thank Florent for conducting today's session. It was very informative. Also thank everybody who has joined the webinar today. Just another reminder that you will receive an email very shortly, in the next few days. Please look out for that, which will give you links for the recordings. And again, please be happy to share that with any of your colleagues. And just another quick reminder, please complete the short survey at the end of this session as you exit, as again, this will give us valuable feedback. So without further ado, I'd just like to thank everybody for joining today, and we look forward to having you join on our next session. Thank you, everyone.
Thanks everyone for joining. Bye.